Chapter 10, Chemical Bonding. So there are different types of bonding theories which explain why atoms bond to each other. Certain theories can explain the shapes that we see for particular molecules. Others can describe whether we would expect a molecule to be magnetic. But we're going to focus on Lewis' theory, which is looking at how atoms are going to share their valence electrons to form bonds. So your valence electrons are your outermost electrons, and we can find those by simply looking at the periodic table and following whatever group number a particular element is in. The governing rule for how we build our dot structures is the octet rule, which says that atoms are trying to get 8 valence electrons to become stable. Noble gases have 8 valence electrons already in their outermost shell, except for helium. So stability is the name of the game. We're trying to become like the noble gases. The elements that will always obey this rule are carbon, nitrogen, oxygen, and fluorine. So this means that when you draw out one of these structures and you have C, N, O, or F, they will always have to have 8 electrons around them. The elements that will typically have less than will be boron. The ones that will always have less than are hydrogen and helium. Hydrogen can never have more than 2 total electrons, which means it can only make 1 bond. An expanded octet is when we have a particular nonmetal as a central atom, and it can have more than 8 electrons, sometimes 10, sometimes 12, and that's okay. Those elements are going to be nonmetals and semimetals that are third row and below. So phosphorus, sulfur, chlorine, arsenic, selenium, bromine, iodine, tellurium, argon, krypton, xenon. Recall that chemical bonds are formed through electrons. Ionic bonds are when we transfer electrons between nonmetals and metals. And covalent bonds are when we share electrons between semimetals and nonmetals. So your Lewis dots, as I said, each dot is going to represent a valence electron. So group 1 has 1, group 2 has 2, group 3 has 3, etc. And we're looking at our main group elements, so our elements 1A through 8A. When we put our dots around a particular element, we always go around clockwise and put on single dots, and then we go through and we start to pair things up. The single dots are showing us how many bonds would an atom like to make. So carbon has 4 single electrons, it wants to make 4 bonds. Nitrogen has 3 electrons, it wants to make 3 bonds, right? 3 lone electrons here. Total is 5, but 3 that are alone. Oxygen has a total of 6 electrons, but it has 2 that are all alone, so oxygen wants to make 2 bonds. And fluorine, who has 7 total electrons, likes to make 1 bond because of its lone electron there. So we can take a look at our group numbers and figure out how many bonds does a particular element want to make. So when we draw our Lewis structures, we're typically going to put the least electronegative atom in the middle. Your central atom will also be the atom that is all alone. There's only one of them. Then you're going to draw lines between that atom and all surrounding atoms. We count the total number of valence electrons by looking at the group numbers. We add electrons for negative charges. So if there was a -1, we'd add 1 electron. -2, we'd add 2. Or we subtract electrons for positive charges. A +1 would mean take 1 electron away. So for each bond in the skeletal structure, it's counting as 2 electrons. So once we've drawn our single lines in between all of our atoms, we place dots, pairs of dots on the terminal atoms, so all the surrounding atoms. And then if we still have electrons left over, we put them on the central atom. If the central atom has fewer than 8 electrons, we can move 1 or more pairs from the outlying atoms to form multiple bonds. So we can make double bonds, we can make triple bonds, but this is not where we start. This is where we would end. So when you start drawing these structures, do not start willy-nilly making triple bonds and double bonds between things. So how can we draw our Lewis structure for nitrogen trifluoride? We have 1 nitrogen, 3 fluorines. We put the nitrogen in the middle because it's all by itself and it's less electronegative. We count our valence electrons by looking that nitrogen comes from group 5 and fluorine comes from group 7. So there are 3 fluorine atoms, so 3 times 7 electrons is 21, plus the 5 from nitrogen gives us a total of 26. We draw our single lines between our central atom and our outlying atoms. We then place dots on everything until we get a total of 8. So nitrogen has 1 lone pair and 3 bonding pairs. That is 8. Each fluorine atom has 3 pairs and 1 line, which also counts as 8. If we do a final electron count, we notice that, yes, indeed, our single bonds, which is each of the line, we have 3 of those, times 2 is 6, plus the 10 lone pairs. 10 lone pairs means 10 pairs of dots, so that's 20, to add up to 26 valence electrons. So this is the correct structure for nitrogen trifluoride. On the carbonate ion, so carbonate is CO3 with a 2- charge. We put carbon in the middle because it's less electronegative, and it's all by itself. So we count up our electrons. Carbon is group 4, oxygen is group 6. We have 3 of those, and then we have 2 electrons, so we add in that extra 2 to get a total of 24. We draw single bonds between all of our atoms, then we put on our dots. Now, when we look at this, carbon has 8 electrons, 3 lines, 1 pair of dots. Each oxygen has 8 electrons because it has 1 line and 3 pair of dots. However, if we did our total electron count, we would see that there are 26 electrons, which is not allowed. So what we do is we would erase that last pair of electrons we put on carbon, and then we form a double bond between any one of the other oxygen atoms by removing a pair of electrons and putting it in the middle to form another line. So it doesn't matter which oxygen you do this with, it's just showing here that one of the oxygen atoms is going to be double bonded to the carbon. Other examples of Lewis structures that have double bonds would be carbon dioxide. So we start with 4 electrons from carbon, 12 total from oxygen for a total of 16. We have our 16 dots here. So when we have 2 pairs of dots between an atom, we call that a double bond. So each of our respective atoms still has its 8 electrons. The oxygens are identical, and carbon has no lone pairs of electrons, but has 4 bonded pairs of electrons for a total of 8. Nitrogen is an example of a diatomic element that will triple bond. So each nitrogen has 5 electrons. 5 times 2 is 10. So now we see that we have 3 pairs of electrons between our atoms to get to our 8. So nitrogen is triple bonded. We have 3 lines, and then each nitrogen has 1 pair of electrons to result in 8 electrons for each atom, giving us then the total of 10 electrons. So we have a triple bond. Certain compounds will have an incomplete octet. For example, beryllium hydride. We have beryllium with 2 electrons. Each hydrogen brings 1 for a total of 4 electrons. So beryllium can only form 1 bond with each hydrogen, and we just show that there are a total of 4 electrons. This is a stable molecule because of the maximum number of electrons that hydrogen can hold and beryllium. Boron trifluoride. Boron is group 3, so it brings 3 electrons. Fluorine is group 7. 3 times 7 is 21, plus 3 gives us a total of 24. We see that boron is in the middle. It's less electronegative, and it's all by itself. Each fluorine atom has 8 total electrons. Boron, however, only has 6 electrons. But carbon, nitrogen, oxygen, fluorine are the atoms that have to have their 8. Odd electron molecules, like nitrogen monoxide. Nitrogen brings 5, oxygen brings 6. We add those up, that's a total of 11. So oxygen has its 8 electrons. However, nitrogen only has 7 because it has a double bond, which counts for 4 electrons, plus the 3 dots. The expanded octet, when we have a central atom that is in row 3 or below, for example, sulfur, is in the middle because it's less electronegative and it's all by itself. So sulfur brings 6, each fluorine brings 7. 7 times 6 is 42. Add those together to get 48. And we see that sulfur has made 6 bonds, single bonds to each of the fluorine atoms. Each fluorine is identical because it has a single bond and 3 lone pairs for a total of 8 electrons. However, sulfur, because it has 6 bonds, which means 6 times 2 is 12, has an expanded octet. This is acceptable for sulfur. Now, those row 3 and below elements, nonmetals and semimetals, are not always going to do this. They are only going to if they have to. So typically speaking, things are going to obey the octet model when they can. So electronegativity is expressing how much an atom is going to pull on electrons within a bond. So it's like a tug of war. Certain elements are stronger than others and therefore will hold those electrons closer to them. So high electronegativity are typically going to be your nonmetals. They really want electrons to become stable. Versus low electronegativity elements are going to be your metals because they'd rather give up electrons. So they're not going to pull onto electrons because that's not what they want to do. So in some ways, we can look at it as a competition for electrons, and the nonmetals are going to be the ones who want those more. And your difference in electronegativity is going to determine the extent of how polar a bond is. So polarity is looking at, just like on a magnet, how you have a north end and a south end. So they're different. So in molecular bonds or atomic bonds, you're looking at something is going to be somewhat positive and something is going to be slightly negative. So electronegativities are listed here, and the most electronegative element is fluorine. And we can see here that our nonmetals are much higher in electronegativity than a lot of our metals. These are not numbers that you have to memorize. These would be provided to you. So our electronegativity increases as we go from the bottom to the top of the periodic table and from left to right. So we've discussed how ionic bonds are always between metals and nonmetals, and covalent bonds are always between always between semimetals and nonmetals. Well, there's a sliding scale that says whether things are truly ionic or truly nonpolar. Nonpolar means that there is no difference in who's holding electrons more strongly than something else. So an electronegativity difference of greater than 2 would be considered ionic. Somewhere between 0.4 and 2 is what we call a polar bond. And between 0 and 0.4, we call that nonpolar. And the way to figure this out is simply to look at each of your atoms and take the difference between each of the respective atoms' electronegativities. So for example, if I go back a slide, if I look at the bond between lithium and fluorine, I see fluorine is 4, lithium is 1, so 4 minus 1 is 3. So that's how we see on our table here where lithium fluoride is. Up here at the top, we see that the electronegativity difference is 3. So compounds that are up here, large electronegativity difference, are going to be mostly ionic. Elements down here that are very similar to each other with their polarities are going to be polar or nonpolar. So polar covalent bonding, once again, happens between 2 atoms that are sharing electrons, and their electronegativity differences are fairly large, so somewhere in between that 0.4 to 2 range. A truly nonpolar covalent bond can only occur when both atoms are identical. So H2, N2, O2, F2, Cl2, Br2, I2. So polar bonds happen when there's an uneven sharing of electrons. One atom pulls the electrons closer to it, which makes it slightly negative. leaving behind the other atom to be slightly positive. So a polar molecule is when you have polar bonds within a molecule and they are not canceling each other out. So we call this a dipole moment. And a dipole moment is shown down here by looking at putting the positive sign closest to the element that is electropositive or the least electronegative atom and drawing the arrow towards the atom that is more negative, so more electronegative. So our dipole moments can be canceled out. Once again, we think of this as if it's a tug of war and who can win? Is there an overall winner in this tug of war? The electrons can be pulled in different ways depending upon what the shape of the molecule is. So in order for you to have a nonpolar molecule, it means that these dipole moments are going to have to cancel each other out. So when we want to determine if a molecule is polar, you're going to draw the Lewis structure, which we discussed at the beginning of this chapter. You're going to look at the dipole moments and identify the electronegativities for each atom. You're going to draw the positive end towards the one that has the lower electronegativity and draw the arrow towards the one that has the higher electronegativity. So if all of these arrows are in equal and opposite directions, that means they cancel out and the bond or the molecule overall would be nonpolar. A simple way to determine polarity for a molecule is simply to look at, are there lone pairs of electrons on the central atom, and are all the bonded atoms the same? If this is true, then your molecule will be nonpolar. If there are no lone pairs of electrons on the central atom, but the atoms are different that are bonded, then you're going to have a polar molecule. If there is a lone pair of electrons on the central atom, then the molecule will be polar. So once again, this is looking at the central atom, not lone pairs of electrons on any of the terminal atoms, because they're typically going to have a lot of lone pairs of electrons. So in practice, when we determine polarity, what you have to do with these is simply look at what are the differences between the electronegativity. So the difference between silicon and chlorine would give us a polar bond. The difference between carbon and hydrogen would be nonpolar. The difference between carbon and carbon would be nonpolar because those are going to be identical. And the difference between potassium and fluorine is going to show that that is an ionic bond. So once again, in order to determine this, you're just simply looking up the numbers on the electronegativity chart and taking the difference between each of them. Now, for our molecules that are listed to the side, I encourage you to draw the Lewis structures and use the rules that say, is my central atom, does it have lone pairs, but all the atoms around it are the same, right? These are the questions that you're asking yourself. Sometimes, like in O2, there is no central atom, but it's only oxygen bonded to oxygen, so therefore it's going to be nonpolar. In number 2, sulfur tetrachloride. When I draw out this Lewis structure, I'm going to see that sulfur once again has an expanded octet, and it's going to show that there's a lone pair of electrons on the sulfur's central atom. So even though I have all the same surrounding atoms, because there's a lone pair on sulfur, this is going to make this molecule polar overall. So in number 3, carbon is going to be your central atom, which means it's surrounded by a hydrogen and 3 other chlorines. Carbon will not have an electron pair on it, but because all of the surrounding atoms are not the same, this molecule will be polar. And in number 4, we have carbon dioxide, where carbon is the central atom. In a previous slide, we looked at the Lewis structure, and it shows that the oxygens are double bonded to the carbon, and those dipole moments would end up canceling each other out. Carbon would not have any lone pairs of electrons, and the atoms surrounding it are identical. So this means that this molecule would be nonpolar.